Lesson 7.4, Similarity in Right Triangles. It says the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original and to each other. So the altitude that we're looking at down below is the segment from C to D. That segment is the altitude. It says the length of the altitude is called the geometric mean of the lengths of the segments of the hypotenuse. So the segment from A to D and from B to D. The length of each leg, that would be AC and BC, is the geometric mean of the length of the hypotenuse and the length of the segment adjacent to the leg. So that's a lot to remember for each of these shapes. Down below, let's get a better look at how to compare the side lengths in these three similar right triangles. In this picture down below, you'll notice that CD is the altitude that connects to the hypotenuse. We've got the big outside triangle from A to B to C. It's a right triangle. And then A from D to C is also a smaller right triangle, and B to D to C is a third right triangle. And they're all similar to each other. But to try to remember the definitions up above, it can be pretty tricky. So what I like to do is assign each segment a variable. We're going to start with the outside on the left, the small leg of the big right triangle. I'm going to call that X. The medium leg is going to be Y. And that inside leg from C to D, we're going to call that Z. So X is always the smaller of the outside legs, and Y is always the longer of the outside legs. Z will always be in the middle. Now where X is on that hypotenuse from A to D, I'm going to call that M. So the shortest little part on that far side is M, the longer side will be N, and the length of the entire thing, we're going to call that P. So now these letters are going to be used to help us create those comparisons that are written in words up above. So let's first start with that length CD. I'm going to call that Z. It splits the part of that big hypotenuse into two smaller sections, M and N. And this ratio is going to be true. M over Z is equal to Z over N. And if we cross multiply here, we're going to get Z times Z, which is Z squared, equals M times N. So that inside segment is equal to the part on the hypotenuse times the other part. And that's one of three connections we're going to be able to make on this picture. Now the other connection that we'll take a look at are those two outside legs, the X and the Y. If we take a look at X, X is going to compare the small segment that it's closest to, that M value, to the length of the entire segment. So if we're comparing side length X, we're going to write M over X equals X over P. So that's going to be, when we cross multiply, X squared equals M times P. So that inside, or that left leg squared, equals part times whole. That whole length for the big hypotenuse. The other comparison that we're going to have, down at the bottom Y, that's going to connect to the N portion of that big segment. So N over Y, that's an N right there, equals Y over P. And that's going to give us, when we cross multiply, Y squared equals N times P, which is also part of the hypotenuse times the whole hypotenuse. Now, these are going to be the definitions we're going to want to memorize. On each picture that we do, or that we work with, we're going to label them with all of those variables. And our goal is going to find one of those three formulas to use, and then we'll be able to solve for our missing variable. Now down below, geometric mean. The length of the geometric mean is always that segment in the middle. So from C to D, that's the length, or that's the geometric mean of that right triangle. We can also utilize Pythagorean theorem because we have right triangles. So down below, if we take a look at each of those side lengths, To use Pythagorean theorem, what we have to remember is this is only for sides, not angles. Let's start off with the big triangle. X squared plus y squared would equal p squared. So that's the big triangle and the entire shape. If we look at the shape that's kind of on the top, well then x becomes the hypotenuse. So now the top triangle on the left is m squared plus z squared equals x squared. And then that bluish kind of triangle at the bottom, that one has y as the hypotenuse. And that one's n squared plus z squared equals y squared. We'll have options of either cross multiplying and getting those formulas up above in red, blue, and green, but we can always default to Pythagorean theorem if that's going to be an easier option. All right, let's see how this works with some examples on the next page. I've zoomed out the picture, but we'll read the directions together. Given that triangle PQR is similar to triangle QSR, find QS, PS, and PR. So what I want to do here is identify the side lengths similarly to what we did on the front. I'm going to first start with the big triangle from P to Q to R, the big picture. I've got PQ as one leg of the right triangle and QR. Notice QR is smaller, so I'm going to call that side length X. That means QP is the bigger leg. I'm going to call that Y. And then from Q to S, that's that geometric mean. I'm going to call that Z in the middle. The 9 on that right-hand side on the bottom is closest to X, so I'm going to call that side length M. From S to P, that's closest to Y, I'm going to call that side length N. And then the entire hypotenuse, I'm going to label that lowercase p. So I know that's kind of tricky with capital P in the picture. Let's see what we can do with that. All right, I'm going to zoom out and let's take a look at QS, PS, and PR. Let's start with segment QS. If we look at QS, that's the geometric mean right there. So we know that Z is connected to M and N on the picture, but we don't know what M and N equal. What I do notice is that side length is also a part of this triangle over here on the right-hand side, and that would be a right triangle. So if I draw that out, Q is on the top, S is on the bottom, and R is on the right. We know that S to R is 9, Q to R is 15, and we're trying to find the length from Q to S, so we'll call that little z. Because this is a right triangle, we can do Pythagorean theorem here. So we can do z squared plus 9 squared equals 15 squared. Now, if you have a calculator, go ahead and follow along. If not, make sure you know how I'm getting the values that I'm getting. For example, z squared plus, well, 9 squared is 9 times 9, and that's 81. 15 squared is 225. So to get z by itself, we're going to have to move 81 to the other side. And we get 144. So we've done this kind of idea before. To get z by itself, I'm going to take the square root of each side, canceling out the squared with the power of 2, and z will equal 12. So that is the length of QS. That equals 12. So I'm going to label that on my picture, and that's our first answer. All right, let's try PS. I'm going to zoom out to give us a little bit more room to work with. All right, there we go. To find the length from P to S, that's that other portion of the hypotenuse at the bottom. If we know Z and we know M on the right, we can use one of our cross multiply formulas. We can say that N over Z is equal to Z over M, because we know 3 of those 4 parts. We don't know what N equals, but we know Z is 12. And then Z is 12 again, and we know M is 9. From here, we're just going to cross multiply. N times 9 equals 12 times 12. Again, if you grab your calculators, 12 times 12 is 144. And if we divide both sides by 9, 144 divided by 9 is 16. That's the length of PS, 16. All right, let's try the last one, PR. If we actually look at finding the length of PR, that's the length of this entire segment. And we already know the two smaller parts, so this is actually going to be super easy. We don't have to cross multiply, and we don't even have to do Pythagorean theorem. We're just going to do small plus small equals big. That's called segment addition. PR is just going to equal 16 plus 9. We're just going to add those two smaller parts together. And we get 25. And that's the length of PR. That one's done. Let's try one more. It says, given triangle ACB, what is CD? So again, I first want to take a look at identifying my picture. In the big right triangle, it looks like BC is smaller than AC, so I'm going to start off by labeling BC X, AC is Y, and then my Z value goes right in the middle. And then because X is closest to that 3.6, I'm going to call that M. Y is closest to 6.4, we'll call that N. And then the entire segment is P. All right, so we're asked to find CD. That's the segment in the middle. We're asked to find this segment. The formula is that segment equals part times part. So I'm going to do N over Z equals Z over M. So the inside segment equals the two parts multiplied together on the outside. N times M, that's going to be 6.4 over Z equals Z times, or over, sorry, excuse me, 3.6. So when we cross multiply, we're going to take 6.4 times 3.6. I know, that's kind of tricky. And then Z times Z is Z squared. So if you grab your calculator, 6.4 times 3.6 is 23.04. And that equals Z squared. So we have to square root each side, and that would give us an approximate Z value of 4.8. And that would be that segment in the middle. So CD is called the geometric mean. The segment that contains the altitude to the hypotenuse has the name geometric mean. That'll be it for our notes for 7.4. We'll finish the rest of the examples in class.